Quartz is the raw material used to make computer chips. It's first crushed, ground and purified in a high-temperature furnace until it becomes monocrystalline silicon with a purity of 99.99%. This silicon crystal is then sliced into 300mm wafers, each just 0.75mm thick. A barcode is sprayed on the back, and a small notch is cut from machines to recognize orientation. These wafers are extremely fragile. A single chip can shatter with the lightest bump. Each wafer costs about $100, but when processed into CPUs, its value can soar to $100,000, making it more than 10 times pricier than gold. However, not every chip that rolls off the line is perfect. Each grid on the wafer must undergo rigorous testing. Defective grids often differ only in performance, so testing software marks each one, classifies them by yield rate, and assigns performance tiers. That's how Intel defines its lineup: i9, i7, i5, and i3 processors, with lower price models having more defective or disabled cores. Inside a desktop CPU lies what we call a chip, one integrated circuit containing 24 computing cores, a memory controller, and a built-in GPU. If you zoom in on one core, you'll see 44,000 transistors, which represent only 0.0017% of the total transistor count. Magnified times 100,000, you can see countless metal wiring layers stacked above transistors, insulated by thin films. Each chip contains hundreds of kilometers of wiring, 5 metal layers per transistor, all interconnected by vias, stacked layer by layer into a single CPU. A 300mm silicon wafer can produce 230 CPU chips, or about 900 memory chips, since memory dies are smaller. Before production, 25 wafers are stacked and placed in a sensor-controlled box. These boxes move along ceiling tracks, automatically delivering wafers between machines. Each machine has robotic arms that pick up wafers for processing, then send the box to the next step. Thousands of these boxes operate simultaneously in a chip fab. The first stage is photoresist coating. The wafer is coated, baked to remove impurities, and then loaded into the lithography machine. There, ultraviolet light shines through a patterned mask, projecting the circuit design onto the wafer via high-precision lenses. After exposure, the wafer is placed in a developer solution, which removes the light-exposed photoresist, leaving behind the etched circuit pattern. The lithography machine is the heart of chip manufacturing. At its base is the UV light source, above it a lens assembly, and at the top the mask like a photographic negative. Light refracts multiple times before shrinking the pattern to 4-pore scale, projecting it precisely onto the wafer's surface. This process, lithography and etching, is repeated for every circuit layer. Each mask is a 6-inch square, holding patterns for 2 CPU designs. The lithography tool effectively copy-pastes the blueprint onto the wafer hundreds of times, writing billions of transistors in minutes. A high-end CPU might require 80 layers, meaning 80 separate masks, each costing $300,000. To keep up with demand, over 400 machines operate simultaneously, producing 50,000 wafers per month, over 10 million chips, and still that's not enough to meet global demand.